with 1 over the rest of the indices without the negative sign. Right? So anytime you have the negative sign, all you just have to do is replace it by 1 over then the rest of the indices without that negative sign. And then, what if you now have the power as a fraction? If you have the power as a fraction, let's say 1 over b, it simply means that all you just have to do is take the root to b of that base. That's what it means. So example of this in simple terms so that it can be clear is if I have 4 to the power of 1 over 2. What I'm just simply saying is to find the square root of 4, right? That's what the negative power, that's what the fractional power does in this case. And then you look at 5, and then you look at 1 and 2, you'd find out that you could combine this, right? So if you have something like a to the power of b divided by c, right? You could split this, and then you could have the root to c of a, and then take the power of b, right? So it doesn't really matter. If you have b over c, it's still a fraction. You could split it in this form, right? In clarity, you could have that if you also have a product of powers. The product of powers simply means operate on one power first, then multiply it by the second power. Same thing happens. Operate on the first power, then multiply it by that second power. Now notice, in this case, what you are simply doing is just multiplying the powers, right? So for simplicity, you could find out that this a raised to the power of b divided by c is just the same thing as a raised to the power of 1 over c times b. So the concept is the same thing. So in essence, do not be afraid to split out your powers. Do not be afraid to operate on those powers, provided that they are obeying the signs of the laws of indices, right? Which is the most important thing. So let's pick some basic examples, and then we'll look at the concept. Of course, we will try as much as possible to pick these 5 concepts at once and then solve questions, a lot of questions under them, so that we will have as much clarity as possible, right? So let's pick those questions. Now, let's do something basic. Let's take 27 raised to the power 1 over 3, right? 27 raised to the power 1 over 3 simply means, by applying the law of indices, the cube root of 27, right? This is what it means. Now, you'll find out that 27 can still be simplified further, right? You could still break it further. You'd have this as the cube root of 3 raised to the power of 3. So 3 raised to the power of 3 represents 27. That's 3 times 3 times 3. That's 3 times 3 is 9 times another 3. That gives you 27. So you have 3 raised to the power 3 in the place of 27, then the cube root covers it, right? Now you'll find out there's a basic concept that we do in secondary school that will tell you that if you have this one, this cube root will cancel this power, right? But in essence, what we are simply doing is 3 raised to the power 3, 1 over 3, right? Remember that by this law of indices, we are multiplying that power. So if you have 3 times 1 over 3, that will give you 1. Right? So that's, in essence, that's what we do when we cancel out these powers, right? So it's not like we just pick a power and then we just pick a root and then cancel them out. It just obeys the law of indices. And then we have our final answer to be 3. Simple and short, right? Let's take another one. If you have 2 raised to the power x to be equal to 32, and then we are to find the value of x, what do? Simply, we just have to look at both sides. The left-hand side is 2 raised to the power x. We can't really work much on that. But the right-hand side is 32. Right? Now, this right-hand side is a big value, so we should be looking at ways in which we can simplify that big value. Now, for 32, we could express it as 2 to the power of what? Now, 2 times 2 is 4, times 2 again is 8, times 2 again is 16, times 2 is 32. So you have this as 2 raised to the power of 5, right? So we have expressed the right-hand side now as a multiple of 2. Now, the base is the same, right? Now, if you have an equality sign, and then the base is the same on both sides of the equality, we can equate the power, right? If you have an equality sign and then on both sides of that equality the base is the same, you can equate the power. So if in this case you now have x to be equal to 5 as your answer. Now this concept is not just limited to the power alone. If you have a situation where the power is the same, you are also allowed to equate the base. Let's see something like that. Let's see how that happens. Let's say you have, if x raised to the power of 3 is equal to 64, find x. Right? Now, you would find out that in basic O level, when you do this, all you just simply do is you say you take the cube root of both sides, right? That's how it works, cube root of both sides, and then you find the cube root of 64. Now, in terms of indices, we can simply do this as what? Express 64 as a simple indices. Now, 64 is the same thing as 4 to the power of 3, right? 4 times 4 is 16, times 4 will give you 64. If this is the case, now the power is the same. So the power is the same, we are allowed to what? Equate the base. So if we equate the base, what would we have? We'll have x equals 4 as our final answer, right? And this is basically how the concept of indices works. It's a very simple concept. The application of the laws of indices is the most important part as far as this concept is concerned. So you must ensure that whenever we apply these laws, we are applying them in the right sense and ensuring that the order of arrangement is maintained, right? The order of arrangement ensures that we do not pick out wrong signs or wrong values in their wrong positions, and we keep them as correct as possible, right? So this is indices as it is. Now let's quickly rush through the next concept, which is the concept of logarithms, right? Now, as our knowledge from O level teaches us, you find out that indices and logarithms have always been treated as pairs, right? We have always considered indices as more like a twin brother to the concept of logarithms. Now, this is in fact very true, because you'd find out that every single concept of logarithm you have can be expressed as their version of indices. Similarly, every single concept of logarithm can be expressed as their version of indices, right? So let's look at those logarithms, and then let's first and foremost try to bring out a relationship between indices and logarithms. Let's see where they connect to, and then from there, let's pick out the concept. Now, during our study of indices, we have found out that it is governed by two major concepts: the concept of the power and the concept of the base, right? Those are the two concepts that guide the study of indices. Now, those two concepts remain very, very true as far as logarithm is concerned. We are still led by the concept of a power and the concept of a base. Now, the only thing that is introduced is the concept of the log itself. The log in this case, which means the logarithm, right? Now, that logarithm is calculated or deduced in terms of the base of operation, right? So the base determines what your logarithmic value would be, right? So that's why you have it that you say log of x to base y, log of y to base z. It's always to that base, right? The logarithm is always calculated with respect to that base. That base is the most important part of the operation. So let's begin from there. Now, whenever we take those logarithmic values, we expect to have a result, right? Just like if we say 3 raised to the power 2, we expect our answer to be 9. Similarly, if we take the logarithm of a value to a base, we also expect to get a value, right? So let's look at a basic definition of what logarithm stands for, and from there we'll push on. So let's pick 3 arbitrary numbers, right? Remember that the core concept of mathematics is always led by the assumption of numbers, right? These letters are just basic letters, right? They just mean that for any number you pick, the assumption will always hold. It's just like a generalization on our part. So let's pick these numbers, and then, of course, indices will tell us that a raised to the power x will give us n, which means that if we take the indices of a number, right, we always have a result. 3 raised to the power 2 will give us 9. 4 raised to the power 2 will give us 16. 2 raised to the power 2 will give us 4, and so on, right? So whenever we take an indices, we expect a result, right? So n is the result of taking the base a to the power of what? To the power of x. Now let's introduce what this means. Now x is now the logarithm of n to the base of a. In mathematical terms, this means x is equal to log n to base a. This is simply the connection between the indices and the logarithm, right? So if we say 3 raised to the power 2 is equal to 9, then we are saying that 2 is a logarithm of 9 to the base of 3. That's how it works. If we say 4 raised to the power 2 is equal to 16, then we are simply saying that 2 is a logarithm of 16 to the base of 4. Right? So if we say a to the power of x is equal to n, then we are simply saying that x is the logarithm of n to the base of a. Right? Now don't forget, a has always been our base. Right? A has always been our base. It doesn't change here. A still remains our base. Simply, it does not change. So when we have a to the power of x equal, we are simply saying x is equal to log n to base a. The base value still remains, right? So this is just like a conversion from indices to logarithms, as simple as that. Now, just as indices has its own laws that guide it, logarithms also has its own set of laws that guide it. So let's look at those laws, and then just like indices, let's also try to apply those laws. Now, of course, we'll start from the basic ones and then move from there. Now, if you remember correctly, when we do indices, two indices where the base is the same and we multiply them, we are simply going to have to what? Add the power. Now, in this case, we are just going to do the opposite of that. In this case, when we now have those numbers and we have the multiplication of those numbers, what we do is we add the logs, right? In